If you're interested in saving a load of money and making one of these £100 light gates for only a few pounds,
or if you want to make an infrared Mission Impossible tripwire,
or you want a snazzy way of counting your money,
or if you want to know if a water tank's going to overflow,
also if you want to know what an interrupt request is,
or see us run a program completely on paper, then you'll want to watch this video. You can use the light gate that we're going to build to measure acceleration, velocity, and we'll also show you how to display the results on a little screen. We're going to take you step by step through the basic code, which only contains a few lines in MicroPython. Then that code and the main component, the brake beam sensor, can be reused in many other snazzy projects, which we will show you. And then it will take you through the more sophisticated version of the light gate, which isn't much longer and contains buttons, interrupt requests, screens, and more.
And if you want to make it portable and bring it out onto the field, then you can also attach a battery to that. And we'll show you how to do that.
We'll show you how to get the parts, how much they cost, how to put the simple circuit together, and you can just copy and paste the code and you'll be good to go.
Yep.
All the resources, code, everything will be on our new website, gurgleapps.com, so be sure to check that out.
link to be in description. Let's start by looking at some parts and prices. These brake beam sensors are the heart of a light gate.
They cost about £2 to £3. Here at Adafruit it's $2.95, and here at the Pi Hut you can get some for £2.60. And these are the 3mm versions, however you can get 5mm versions, both will work fine. And also down here it says that it works off 5 volts and 3.3 volts. So this price is a lot less than the usual £100 or more it would cost to buy an actual light gate.
The basic idea is that there's an infrared beam going from here to here, and when that beam is broken by something like a piece of card, we know about it.
The way we know if the beam has been broken or not is through this yellow wire here. Yours may be a different colour, like white. The other wires are pretty straightforward. Red to positive and black to negative on your power source. Same for both sides.
We'll be using these to make a light gate, but there are so many other uses of these brake beam sensors. For example, you could make a burglar alarm, so if someone walks in your room and breaks that infrared beam, then an alarm could go off, or you could get a notification or text message. Or let's say you want to know when a certain level's been reached in a water tank. Beam has just been broken. I'm going to stop because it said max water level reached. You could do a smoke detector, so thick smoke breaks the beam. Or you could use it for counting things, so when the beam is broken, then the count goes up 1. So you can count people, money, coins being dropped into a money box. The possibilities are almost endless. But we're just going to be using these to measure acceleration and make a light gate. But the first super simple code and circuitry that we're going to show you can be transferred to almost any simple brake beam sensor project, like the ones we've just been showing you.
This is what we used in our experiment to hold the brake beam sensors apart. You can see it's just one of my brother's old toys.
You can make something similar with just some lollipop sticks, or I'm sure you guys have plenty other ideas. To keep it simple, we're just going to use a mint tin and attach them using some sticky tack or blue tack like this. Now for the circuit. Don't be scared off though, this is super simple. Breadboards only cost pence and pounds, and this microcontroller on the breadboard is a Raspberry Pi Pico, and you can pick this up for about £3.60, which is about $4.
Like I said earlier, it's really simple. I've got my microcontroller here, and this one here is the sender, and that's simply connected to positive and negative. And the receiver one here, same thing again, positive and negative. But the wire that sends us the information, we've connected it to GPIO pin 15. Well, let's check that out on the breadboard.
If you don't know how a breadboard works, then we have a video on that. And the microcontroller board that we've got is a Raspberry Pi Pico. Any other RP2040 board would work fine. We're going to be coding in MicroPython, so as long as your device is compatible with MicroPython, you should be good to go. We soldered some header pins onto our Raspberry Pi Pico. There's a video on that if you were interested. So it's easy just to slot into our breadboard and we're ready to go. I'm going to select this pin here, which is a ground pin. So I'll select that. And then I'm going to connect it here. And this whole column here is connected. So this can be our negative column. And this pin is my 3v3 power. And I'm going to connect that to this column here. And this can be our positive column. Now to connect up the sensors. This one is pretty straightforward. Red to positive, so that goes in this column. Then black to negative, so that goes in this column. Now for this sensor, same again, red to positive, black to negative or ground. The final wire I need to connect is this yellow one, so I've just chosen GPIO pin 15 here. And that's our circuit.
We're using a Raspberry Pi running Funny to get the code onto our microcontroller. If you don't know how to do that, check out our website and YouTube channel. You don't have to use a Raspberry Pi and Funny. We're just using it because it's cheap and accessible.
We pre-written the code because it would take a bit too long you watching us type in the code in real time. Line 1, 2, 3, we're just importing the things we need. This line here, we're just setting the beam pin. That's a spare wire on our break beam sensor that tells us whether the beam's been broken or unbroken. We've set that to GPIO pin 15 on our microcontroller. This line here, we're just creating a variable called old beam value. The value function gives you the value of the pin that you've given it. So it'll either be on or off, true or false. In our case, we've given it beam pin, so the value of beam pin will now be stored in this variable. Next, we're creating an infinite loop, and in that loop we're saying if old beam value, which is the variable we just created, is not equal to the beam value right now, so that's if it's changed from being true to false or false to true, then we set the old beam value to not itself. So if old beam value is true, we'd set it to not true, which is false. If it was false, we'd set it to true. Then we're just printing old beam value. Finally, we're just sleeping for 0.1 seconds. To give you a better understanding of this code, I'm just going to demonstrate it. So, put my hand through it. It's false, because the beam's been broken. True.
Here I've used the code my brother has just shown you and have altered it slightly to fit in with this project. So as I drop a coin into this Lego box, it increases a counter and prints it on the screen. It's similar to the code before, but I'll explain the differences. So line 7, we've created a new variable count, which is set to 0 since no coins have been dropped into the box. Then, instead of printing old beam value whenever it's changed, we're checking what it's changed to, and if it's changed to true, then we're going to increase our counter by 1 and then print it. So the counter should increase by 1 each time a coin is dropped into the box. The reason we go from false to true is because when we insert our coin, we break the beam, so it's false. Then when we release it, the beam is resolved, so it's true. And we increase our count and then print it, so we can see it's 1. Incidentally, when I drop that coin, you can see it goes quite fast. So in the code, we've changed it from sleeping from 0.1 seconds to 0.01, so it has time to recognise when a coin has been dropped.
I've just opened up the code in VS Code so then I can have 2 windows open at once. This code on the left is our code we did earlier, so not the coin dropping one, the code before that. The code on the right does the exact same thing to the code on the left. What we've done in the new code is we've used an interrupt request here. And I'm just going to briefly explain it in this video, but if you do want to know in detail about an interrupt request, I think my sister's explained that in our retro encoder video, so go check that out, link should be in the description. All you do is give the interrupt request a trigger, so a thing to set the request off, and a handler, the thing you want it to do, in this case our beam change function. And instead of checking if the beam's been broken, checking again, here, if the beam has been broken or resolved, it runs the beam change function. When you keep checking if something's changed, that's called polling. Using an interrupt request, we'll watch out for a change on a pin, and when there is a change, it'll run a function for us. The reason we do this is because it's really important that we don't miss a change in that beam. We're talking fractions of a second. Now we need to time how long the beam has been broken for. So I've just created a new variable up here called last time, and in that is the time in microseconds right now. Here I'm just turning last time into a global variable so I can use it inside this function. Then we're saying if the beam is not broken, we're going to create a variable called elapsed time, and in that is the difference. So this times.ticks underscore diff gives you the difference between 2 times, and we're having the difference between the time now and last time, which was the time up here. Because that's in microseconds and we want it in seconds, we're going to divide that by 1,000,000. And then we're just printing beam restored and the elapsed time. If the beam is broken, we're just going to change the variable last time to the time it is right now. So briefly, when the beam gets broken, it remembers that time, so that when the beam gets resolved, it can use that time to find out the difference. Now we're just going to run the program to see if it works. So I've just opened up Music Practice Toolkit and got this metronome beeping every 1 second. So plot the beam. 1, 2, 3, 4, 5. It works, great.
Now the code gives us the time that our beam has been interrupted for or broken. Using that information, we can work out speed. Well, how can we do that? Speed is equal to distance in meters divided by time in seconds. So let's say we want to find out the speed of this little toy car of my brother's. We know what the time is. That is stored in a variable called elapsed time, and that time is equal to the duration of time from when the beam gets broken, and then the car will pass through, and then when it's resolved. The only other bit of information we need is distance. And the distance is just the length of this card, because that's what's going to be passing through our brake beam sensors. And I've measured this to be 35 millimeters. The distance just has to be in meters, so we'll just convert that. To convert from millimeters to meters, you have to divide by 1000. So 35 divided by 1000 is 0.035 meters. And I've popped that into our equation there. That's all there is to it. We'll put that into the code and measure the speed of this car.
I've just set up a variable called velocity, which is 0 right now. And I've also set one called distance, which is the distance of our card, which is 0.035 meters. And then obviously I need to make those variables global. All that's left to do is the formula. So velocity equals distance over elapsed time. And then I just print that here. So let's use our new code and find out the speed of my toy car. So I've got the 35mm card here. I'm just going to push it through our brake beam sensors. The car was going at 0.64 meters per second when it passed the brake beam sensors. I want to find the acceleration of my toy car. The acceleration is the change in two velocities divided by the time. Now here we've only got the chance to work out one velocity, so I've made this new piece of card. So we're going to work out the velocity from A to B, and then the velocity from C to D. And then we're going to divide that by the time taken from B to D.
The best way to explain this code is by running through it in your head or on some paper. So that's what we'll do now.
This is the light gate, car, main variables, and code.
We're in this infinite loop until something happens on our light gate.
Car moves, beam is broken, so our beam change function is called.
The beam is broken, so we're going to skip all this and just run this one line. Well, let's say ticks US is 3 million. Well, we need to store that in the variable last time. 3 million, M for million.
And we finish the function, so nothing happens until the beam is restored here. So now we're at B, and the beam has been restored.
So now the beam is not broken, so we've got to do this code. So elapsed time is the difference between the time now and last time. Let's say the time now is 10 million microseconds. So we'll do the 10 million, take away the 3 million last time, gives us 7 million. Then we divide by a million, so we can just remove this million here. Now we've got to do this if the mode is waiting, and it is. Time at B is the time now, which we said was 10 million microseconds. So we'll put that in our time at B variable. And now we've got to do velocity 1, which is the distance, so up here in this variable is 0.035, divided by elapsed time, which up here is 7. Yeah, our cat just walked through. So that's 0.005. Lastly, we set mode to mode past B, so I'll swap that out. We don't have to do any of this or any of this, so then we're out of our function. Incidentally, if this was if mode is past B, then we would get to here, because now it is mode past B, as you can see there. But this elif is joined to this if, so it won't even get run.
So nothing happens until the beam is broken again.
We've been here before, we don't have to do any of this because the beam is broken. So we just remember last time. So we just set last time to the time takes US. So let's say that's 16 million microseconds. and we exit our function again.
Until the beam's been restored again, here.
And now the beam is not broken, so we do the elapsed time thing again, so the difference between last time and the time right now. Let's say that's 21 million microseconds. So it's 21 million minus the 16 million, which is 5 million. Okay. And then we divide that by a million. So it will just take the million off. And this time it's not mode waiting, so we skip this and we go onto our elif. And the mode is mode past B, as you can see here. So we'll do all this. So the time at D is going to be the time right now, which is 21 million microseconds. So we'll put that in our variable. Right. Velocity 2 is distance, which is 0.035, divided by elapsed time, which is 5, and that is equal to 0.007. So acceleration time is the difference between the time at D and the time at B divided by a million. So the time at D is 21 million minus the time at B, which is 10 million, which will give us 11 million. Sorry. Which I've put here. And then divided by a million, so we'll just take away this million. We set our mode to mode complete. Then acceleration is velocity 2 minus velocity 1, which is 0.007 minus 0.05, which gives us 0.002. And then we divide all that by acceleration time, which is 11. And my calculations give 0.00018 recurring.
So we get how that works without a computer, so let's do it for real. Let's test this out by measuring the acceleration of my toy car. The acceleration was 0.47 meters per second squared. I don't like this. All I've done to fix that is just simply in our beam change function, before we do any of the gump, I've just made an if here saying if the mode is complete, so that's if everything's been done, we just return. So that means we just exit our function. That's simple. So now let's test this out. You can see I've measured the acceleration here, and no matter what I do here to break the beam, nothing changes here.
Next, I'm going to add a little nicety. So at the moment, after we've taken one acceleration measurement, we have to restart the program if we want to take another, which is a little bit of a hassle. So I'm going to add a reset button. So I just have a push button switch here. Then I've got two wires connected to either side of the push button switch on a breadboard. I've connected one side to ground and the other to GPIO pin 1 on my microcontroller. The first change we made to the code is set up GPIO pin 1, so that's what we're doing on this line here. Next, we've created a function here called reset, and this is just setting what we want to do when the reset button is being pressed. So setting all these variables back to 0, and then also setting the mode to mode waiting, like at the start of the program. And we're also just printing reset. Then down here we have an infinite loop, and we're just polling every 0.1 seconds, just because all we're looking out for is a press of a button, and that action doesn't happen within tenths or less of a second, so we can afford polling. So when our button's been pressed, the value of the reset button will be 0. So here we're just checking, is the value 0, so has the button been pressed? And if it has, then we'll run our reset function.
Let's test this out. So I measure the acceleration of my toy car once, 0.05, Normally I'd have to reset my program now, but all I have to do is just click and everything's reset, ready to do the experiment again. Oh gosh. Oops, it went by accident there. I'll reset it again. Oh, triple click that. Okay, measure it again. And then if I want to measure it again, I just reset again.
The next nicety I'm going to add is this little screen here to display our results on. This is an SSD 1306 OLED display. I have a video on these and these are really useful, extremely cheap, only a few pounds, and they come in other sizes as well. This one has 4 pins and I've just connected them to some jumper wires. I'll connect this one to ground, next one to the positive column here. I'm going to connect the clock pin to GPIO pin 5 and the data pin to GPIO pin 4. Now onto the code. So the first changes that we've made is we've just set variables clock pin, data pin and bus, and we've just set them as whatever their GPIO pins are. And the bus is just, if you look on this diagram here, we're using GPIO pin 4 and 5, and if we follow along here in the blue, there's 0 and 0, and that's just the bus. We've used these variables here, here, and here. And this line really is just setting up our SSD screen. And then on this line, we're just setting up the display. So 128 and 64 are just the dimensions of our OLED display. If yours is a different size, you might want to change those values. And also we have I2C. Yours could be an SPI. All I2C and SPI means is just how this OLED display communicates with your microcontroller. The most noticeable difference in appearance is that the SPI has more pins, whereas the I2C only has 4, as you can see here. Here we're just displaying a rectangle, and its dimensions are 128 by 64, which is just the whole screen. And then here are just the coordinates and positioning of where we want that to be. The reason that this is here, I just like to think of it as if we want to change what's on the screen at the moment. Let's say we wanted this to be 3.0, then the 3 would be written over the top of the 0. So it would all get really messy. So I just like to think of this as just clearing the whole screen. And then without this display.show, nothing would happen on our screen. So that's why that's there. Next, we created a function update screen. So we've got our nifty little line. We like to think just clears the screen. Then we're just displaying some text. So in this case, this will be vel1 colon. And then here we're just also printing whatever's in the variable velocity one. And we've made that a string because that's what we have to pass this function. And then here, just the coordinates of where that text is going to be placed. These two lines do pretty much the same thing, but the text is different and so are the coordinates. And then of course we've just got the display.show so that this appears on our screen. We've used this function here on this line in the beam change function. So once we've got to the point where we've worked out all the velocities or the acceleration, we run this update screen and this will just print first velocity, the second velocity, and then the acceleration measured, which is what we want to find out. Those are just the key bits of information we thought were important. Finally, we've made a few changes to our reset function. We've got the line that we like to think of as clearing our screen, and we show that. Then we are just displaying the text reset with a little smiley face just right in the center. That's where those coordinates are. We're just sleeping for 1 second because I want that reset to be on the screen for about 1 second just so we can see it. And then we're running our update screen functions. So at that point, since all the variables are 0, we should get this screen here just to show that everything's been set back to 0. We'll just give that a little run through and then I'm just going to pass my finger through the brake beam sensor. Okay, there we go. And we've got our first results measured. So we've just got vel1, first velocity, vel2, second velocity, and the acceleration that's worked out. Then I'm going to press the reset button. And we've got our little reset and smiley face for 1 second, and then we're all set back to 0. So it all works. Before we do our final test, we did mention at the start of the video we'd show you how to take this out into the field. So I've just saved our code as main.py and put it onto my Raspberry Pi Pico. Now I'm going to unplug it. Don't need that, and you can see this is all nice and self-contained. And then I've just got a battery pack with 2 1.5 volt batteries in. So in total it'll be giving out 3 volts. So I'm going to connect the positive side to the VBus pin on my Raspberry Pi Pico here. Then connect the negative side to the ground column on my breadboard. I could just connect this to a ground pin. Nice and self-contained, and if I pass my finger through the beam, you can see we've got some results here, and I can press the reset button and it all is powered and all self-contained. So we could just take this and transport it anywhere we like.
I've got a piece of card here attached to my sister's skateboard, and she's going to ride it down the hill, and I'm going to measure the acceleration. Okay, 3, 2, 1, go. It's quite hard to see on camera, but the acceleration was 0.8333.
That's for light gate done. Of course, you can put this in a box or a case to make it more transportable, so you can bring it out in a field or something. Like I said earlier, check out our website, gurgleapps.com, to get information about this project or any others.
Thanks so much for watching. We use this light gate in the video where we explore Newton's second law through experimentation, so if you're interested, then please do check that out. We really hope you enjoyed this video and learnt something new.
If you like this, please give it a big thumbs up and subscribe to our YouTube channel. Have a good day. Bye.
Bye.